So we've looked at integration by substitution and how we'd apply this to definite integrals. What I'm going to do here is I've got a couple of questions for you to have a crack at. I'm going to show you the questions. I want you to pause the video, have a crack at them, and then come back and check your answers with what I'm going to show you here. So here's the questions. 3 simple integrals for you to do, all with limits, all in terms of x. Last two I've given you the substitutions to use. Pause the video and have a crack at them. So the first one was the integral from 0 to 1 of 15x squared bracket x cubed plus 1 to the power of 4 dx. Now the first thing we have to do is we've got to realise we're not given the substitution to use here, as we quite often aren't, so we have to figure it out. Now remember, we always go for the highest power, so in this case it's the x cubed, but because it's part of a bracket, take the whole bracket as our substitution for u. So I'm going to set u equal to x cubed plus 1, and if I take the derivative of that, I get du equals 3x squared dx. Now, if you look here, this will get rid of the x squared and the dx, but I've got a 15 here. Well, remember 15 can be written as 5 times 3. So if I was to factorise it in that manner and put the 5 outside the integral there, I'd have the 3x squared dx that I'm looking for. So I can then transform this integral to look like it would be 5 times the integral of my u to the power of 4 du. So I can get rid of it that way. Now the next key thing we have to do is look at our limits. Now remember here, they're given in terms of x, so this 0 and this 1 is in terms of x equals. To get our new limits, what I have to do is substitute them in here. So if I pick x is equal to 0, my lower limit, let's call it u1, is going to equal 0 cubed plus 1, which is 1. If I then pick my higher limit, x equals 1, what I'm going to do is substitute that in and get my upper limit u2. I'm going to have 1 cubed plus 1, so 1 plus 1, 2. So my new limits from my new integral are from 1 to 2. So I'm now going to integrate it, substitute my limits in as I would, and see what I get. So what I'm going to do is I'm going to end up with 5 times the integral, which gives me u to the power of 5 over 5 between 2 and 1. Substituting in, that gives me 5 brackets 2 to the power of 5 over 5, take away 1 to the power of 5 over 5. Now for this, I can multiply in the bracket by the 5 and cancel out the over 5s. What I've then got to do is put 2 to the power of 5, take away 1, so rewrite that, 2 to the power of 5 minus 1 to the power of 5. We know that 2 to the power of 5 is 32, so 32 take away 1 gives me 31. So the value for my integral there is 31. Next one was the integral from 0 to 3/4 of x over the square root of 9 minus x squared dx. And I'm telling you in this one to use x equals 3 over 2 sine u. So when you get given this one, you don't even have to think about the substitution, we just have to look at the steps. So first thing I'm going to do is I want to eliminate everything with an x in here. We need to find a dx, so just take the derivative of that, and what I get is dx is equal to 3 over 2 times cos u du. So that gets rid of that part there. I can use this and substitute it in on the top here, and I'm going to do the same on the bottom. But this bit on the bottom is going to simplify. So if we look at that and just focus on simplifying it, what I'll get is 9 take away 4 times this squared. Well, if I square the top and the bottom of this fraction, I'll get 9 over 4, and then I'll get sine squared u. So I can take this bottom part, factorise the 9, and I'll get the square roots of 9 bracket 1 minus, so I've taken the 9 out, and I've got 4 times 1/4, they cancel out, times sine squared u. What I can then do is simplify this, so take away the square root of 9, so I've got 3, that's then times the square root of 1 minus sine squared u. Remember from your trig identities, 1 minus sine squared u is cos squared, so square root of that will then let me write it as 3 cos u. Stick all of this back together in my integral, becomes the integral of x, so 3 over 2 sine u, over the square root of 9 minus 4x squared, which we've rewritten as 3 cos u. And that's du. Now we still have to do the same as we did before. We still have to get rid of our limits to get our new ones for u. Well, to do that, I rearrange this. What I'll end up getting for that is if I take the 2/3 across and then the sine, I'll get sine minus 1 of 2/3 x. So what I can then do is substitute in the values of x here to get my two new limits. So if I substitute x equal to 0, my lower limit, u1, that's going to be sine minus 1 is 0, well, that's just going to be 0. If I substitute in the second value of x, so x is equal to 3 over 4, my second limit, u2, that's going to be given by sine minus 1 of 2/3 times 3/4. So that's going to be given by sine minus 1 of, well, the 3's cancel out, I've got 2 over 4, so sine minus 1 of a half. Calculating that gives me an upper limit, u2, of 30, so 30 degrees. Now, what we're going to do is we're going to work in radians in this question. So instead of 30 degrees, what I'm going to represent this as is pi by 6. So I've got my new limits from my integral here. So I've got the limit 0 to pi over 6. If I simplify what's in here now, I've got 3 over 2 divided by 3. So what that'll then give me is a half, but I'll put that out the front, times the integral from 0 to pi over 6 of sine u over cos u. So it's tan u du. So what I now have to do, integrate this here, calculate between my limits, and I'm laughing, I've got my answer. We know one of our standard integrals, integral of tan x, that's equal to negative ln of cos x. So all I need to do is transpose the u into that, and I get a half bracket negative ln of cos u between my two limits at pi over 6 and 0. Substitute in the values, and I can then calculate my answer. So I get 1/2 bracket negative ln times cos of pi over 6. Take away negative, so it's going to become a plus, plus ln of cos of 0. Calculating each of these parts, what that then gives me is a half times, well, cos of pi over 6 is 30, negative ln of 30, well, ln of 30 is equal to 0.1438, so negative of the negative gives me a positive, so I get 0.1438, then I'm going to get plus ln of cos 0, cos of 0 is 1, ln of 1 is 0. So essentially I've got a half times this. If I multiply that through and get it, what I end up getting is 0.0719 to 3 significant figures. Make sure you choose a sensible rounding when you're doing this sort of question. Last question was this one here. So integral from 0 to 1, 6x minus 1 e to 3x squared minus x dx. And again, I'm telling you to use u equals 3x squared minus x. So if I use u equals 3x squared minus x, take the derivative straight away, and I get du equals 6x minus 1 dx. So bonus to that, I can now get rid of this part and this part, as well as the power. So I can rewrite it essentially quite nicely as the integral of e to the u du. Now all I've got to do is calculate my new limits. So if I take the lower limit, x equals 0, and substitute it in, I get a new lower limit u1 of 3 times 0 take away 0, so 0. And if I take the upper limit of x equal to 1, I get a new upper limit u2 of 3 times 1 squared, so 3 take away 1 So I get an upper limit of 2. So what I can now do is change my integral to include these new limits, so it goes from 0 to 2. Now I've just got to integrate it and go on. Well, the integral of e to the u is just simply e to the u, and that's between 0 and 2. So if I substitute these values in to calculate my value at my limit, I get e to the power of 2, take away e to the power of 0. We know anything to the power of 0 is 1, so I'll get e to the power of 2, take away 1. If I wanted to, I could plug that into a calculator depending on what the question asked in terms of the format of the answer. And what that would give me is 6.389. Then the number continues on. So if we went to 2 decimal places, I'd get 6.39 as my solution. So it's the same set of steps every single time. Key parts we have to remember is 1, what substitution we choose. 2, getting rid of everything that involves an x beyond that. So that includes the dx and writing it in terms of u. And 3, making sure we get the limits in terms of u using the previous limits in terms of x. That's a vital part. If we integrate and keep the limits the same, we're integrating with respect to a different variable than the limits are written in, so we'll get the wrong solution and it won't be worth the fuss.